Hey, all right. We got like a minute or two. No, we got like 30 seconds or so before we actually got to start. So I don't know. I'm gonna just say hi. We got our final exam coming up, and this is obviously honors physics. You know who you are. There we go. Just want to make sure that light turned back on. I'm gonna get my Remind open so that if you got any questions you want to ask through Remind, you can do that, and that way I'll get pop up. I don't have to like open it up again. All right, Remind is set. So good evening. A couple more little windows to get in place. All right, morning. Wait, how's it going? So like I said, we got our final exam coming up, and you're watching this because hopefully you want to do a little bit better on your final exam. Maybe ask me some questions, get some tips and hints. I will say this is a good start. This is a great place to be because I was preparing for this, looking at the test, looking at what you got to do, what you've learned, and what I think you've learned over the last couple months. And I definitely think I could help you. So this will be a good use of your time. I'll say it again, having this on in the background and while you're doing something else probably is kind of a waste of time. Like you might absorb something on accident, but you kind of want to be focused for as much as you can be. If you need to take a break, unless you really, really, really want to stick with it live, you can, I guess I can't move that thing. Then you certainly can pause it. That's kind of the beauty of YouTube, is you don't have to be live. That's why I'm doing this a Sunday night before. I know a few of you have your test on Tuesday and some of you on Wednesday. Some of you got it on Thursday. And so like this is kind of early, but that's okay. This is on, you can always go back to this and check it out. So yeah, and I'll say this too. I've talked to people about my review sessions, live streams and stuff like that. And I've heard that they help. I've heard that they don't help. I've heard that it's nothing like what's on the test, and that might be true. It's not. I give you like I can't. I'm not going to give you the test. I'm going to give you like the information so that you can do well on the test. If you do the review guide, that's awesome. I think it's helpful. That's why I have you do it. But it's not like a pre-test. It's not a pre-test. It's like this is the kind of stuff you need to know for the test. So take that for what it's worth. This is part of the building up of your knowledge base so that you can do well on these tests. So, all right, let us continue. Let's take a look at what we got here. So semester 1 was the 4 units. Mechanics is basically the shorthand term for all this stuff. Is all the stuff that moves and forces and velocities and accelerations and stuff like that. So we're going to get into these 4 subjects, and just, let's just get going. Because if you got any questions at any time, you can put it in the chat for YouTube. You could put it in Remind if you don't, if you're not able to put it in YouTube, you just don't want to put it in the YouTube chat, that's all fine. Whatever. So hopefully I answer your questions, and I'm going to stick to the units as best I can. But if you miss it, there's a delay. It's like a 10-second delay or so. So if I've already moved past the question you're going to ask and you're still typing or whatever, that's cool. I could go back. It's not a big problem. So, all right. So let's start. All right, Kinematics in Motion, Unit 1, way back in the early days of sophomore year or whatever. So when you're graphing, this is really kind of in general, what variable is plotted on the y-axis? And so, hopefully you know that the y-axis is the vertical, the one, y and then x. Oh, and I apologize too. I still am fighting a little bit of a cold, so if I sound a little stuffy, or if I sniff or sneeze, I apologize. It doesn't make for good streaming, but it is what it is. Okay, so what goes on the y-axis? Why am I telling you this? Why am I asking this? Guess what? It's going to be on the test. All right, so just remember that. Now, is it going to be this exact question? Probably not, but you got to know this stuff. So what is going to be on the y-axis? The independent variable, the dependent variable, the constants, or it doesn't really matter. And so since I'm asking it, it does matter. So it's not going to be that. Constants, well, what's the point of graphing a constant? You would just get a straight line. And so it really boils down to one of these two. It's a 50-50 choice. If you get it right or not, if you don't know, you could just guess. So, but the answer is the dependent variable goes on the y-axis. So the x-axis is going to be your independent variable. That's going to be the one that you change. So basically you're seeing like, and here's your dependent variable. So it's basically like as like time goes on, or as we change something this way, what's going to happen to the dependent variable, the thing we're looking at. So that's how it goes. So short answer, dependent variable on the y-axis, independent variable on the x-axis. All right, write that down. It's good to know. Okay, now getting into a little terminology. Speed is one of those things we all know about. You knew about this before physics, but then we kind of like, I've said this a few times, we really want to be deliberate in how we use our words to describe things and events and just things. deliberate use of words. Sometimes we forget our words. Phenomena, that's what I was looking for. So how would you define speed? What is the most accurate way to define speed? Now, how fast you're moving, it's fine. That's an okay. That's not necessarily the most accurate, or at least the most descriptive. It's fine. Most people would agree. That's a good definition. Your displacement divided by time. What does that mean? Well, let's see. It's like d divided by t. That sure looks like velocity or speed. Kind of. Yeah. Okay. That's a decent definition. Honestly, I'll take it. Probably though, the bestest everest definition, I'm not saying memorize this because these are all good, but really what we're describing is the rate at which distance is covered. It's not just your displacement. It is your displacement, but it's also just like it's displacement over the change in time, how much time has passed. It's not like the time that I don't know, there's like we're splitting hairs here, but that's the best definition. The time it takes to go a distance, that's definitely wrong. That's like the upside down version of it. Yeah, C is the best way to do it. They're all good, so don't get me wrong. They're all good, but and I'm not even saying there's gonna be a test question just like this, but going in with a solid definition of what speed and velocity is going to be helpful to you on whatever day you take your test. All right, so there we go. If you have any clarifying questions, please ask. I'm just going to keep moving because we got an entire semester to talk about in this, hopefully less than an hour. We'll see how it goes. What is it? 7 o'clock? 7:07. How did that happen already? All right, because I like to talk, I guess. Okay. Ureli is in a hall. I just made. She's in the hall without a pass and is being chased by a security guard again. This is the graph showing her position as she attempts to elude them. So this is the position versus time graph as Ureli moves around in the hall. So if you think about a long time ago, in fact, I think it was the very first day. Ooh, we already got answers. Think about, what was that, walk the line, where you had to actually get in front of the sensor and you had to hold the little board up and you had to move back and forth. That's what's going on here. That's what this position time graph is all about. It's graphing the position, her position, as time goes on, right? So what point does she have a negative velocity? A and C. Interesting. Great choices. One of those is correct and the other one is not. And that's why I bring this up. All right. Velocity. Okay. Velocity is changing a position. So which one shows a negative change in position? And the answer to that is A. All right. If you remember that velocity, and we kind of just talked about it, is your change in position, distance, whatever you want to call it, over time. Then this is just other ways to think about it, right? So this is not necessarily the only way to think about it. There's quicker ways. I'll tell you like a quicker way to think about it in a minute. But she starts out here, she ends here, and ends there. She had a negative change in position. If you guys who said C, that's a great answer. But in this case, because you said it, I know why you said it, because it's in the negative quadrant. But that's just saying she started in the negative somewhere location, and she actually changed her position in the positive direction, which means this is a positive velocity. And if you remember, there was one thing that we associated. If you have a position time graph, if you have a what's called a well, we'll call it a distance time graph, aka a position time graph, is basically the same thing. Velocity is, remember this, slope. All right, velocity is slope. You could put like an asterisk by that. It's my terrible asterisks. Velocity of a position time graph, it's got to be of a position time graph or distance time graph. Velocity of a position time graph is slope. So we have a negative slope, which means a negative velocity. All right. Now, when we get into velocity time graphs, the slope of that is acceleration. So that's a little bit different. Hey, what's up? Got a question? Maybe. So for a position time graph, because like, what's your favorite food? Neither the time, maybe it's the place, but it's not the time. I can answer that later. I know somebody already asked me that. It's what I don't know my favorite food. Oh man, I'm so easily derailed. Don't do this to me. Yeah, the slope of a position time graph is velocity. I'll just leave it at that. All right, my favorite food. I have many favorite foods. I just ate a burrito, homemade, delicious. All right, same scenario. At what stage or stages is she running back toward where she started? Ooh, back toward where she started. What would you say? Where? So again, picture this as a mentally picture this. If you're holding a little board and you're moving back and forth in front of you, remember that from like a long time ago, back when it was still warm out, and all that. At what part would you be heading back toward where you started from? Actually, I'll give it. It's more than one. So she started at like whatever number this is. If this was an actual number line, this would be some number right here. Okay. E is one of them. Yep. There's another. Not D. C is the other one. So C. So look at, she started at some number X. She got all the way. She went backwards, or whatever you want to call it, in the negative direction. She ended at some other number. We'll just call it, I don't know, we're just going to call it Y because we're doing like just random numbers, variables. And it has nothing to do with the X and Y axis, just random numbers. She started at X, she ended up at Y. And now at C, she's heading back, like the position is going from Y to back, she's heading back toward X. And then the same thing at E, all right? C is, yes, E and C are the two places, the two parts of the graph where she's heading back to where she started. If you're standing somewhere and you just call this spot, like I'm standing at number 5, if you're like at a number line, if you're standing on a number line, we'll call it 5, and you run backwards, this looks like it might be -5, right? And as soon as you start heading back, you're at like -4, -3, okay, -2. You're heading back toward 5. So again, this is a position time graph. It's graphing your position as time goes on. I'll clarify anything you need. Got a question? All right, moving along. What stage or stages is she not moving at all? Not moving at all. Her position is not changing. I know you got this. I'm just going to tell you. Yeah, it's D. All right, it's D. She's not moving at all. Her position, and good. Also B. I was going to get to that. So her position is not changing at D. Her position is not changing at B. So both of those, she's not moving at all. And again, you got to remind yourself, is this a position time graph or a velocity time graph? Because you're going to see both. Now you're familiar with both. This is a position time graph. Her position is not changing. It's whatever it is at B and D. It's not changing. All right. We ran into this problem a little bit with the practical. Several people confused velocity time graph and position time graph. It's an easy confusion. I get it. But just remind yourself, what is it graphing? It's graphing position. Position is either changing or it's not. At what stage or stages is she moving with a constant speed? Not a trick question. Constant speed. Again, it kind of harkens back to our practical that I finished grading again. Yeah, ACE. Good. Constant speed. For constant speed with a position time graph, you can replace the word speed with slope, and you're good to go for a position time graph. So A, C, and E. And I purposely underlined the word moving. She has to be moving because I've said it before. 0 is a speed. So, I mean, you could say, well, B is constant. Yes, it is. So is D is constant 0. But I just clarified, the question is clarified to say she's definitely got to be moving. So ACE is R. R's A and C and E are the correct choices for this one. All right, one more little scenario, or one more little question about this scenario. At what stage is she moving the fastest? How would you figure that out? Well, remember, velocity or speed, it's not E, is slope for a position versus time graph. So position versus time graph. So what you got to do is you got to look at where is the steepest. What has the highest slope, whether positive or negative, it doesn't specify. Okay. I mean, it's okay. Whoops. I've said it before. Whoops today, no whoops later, right? So what is the steepest slope? All right. Yep. That's okay. That's why we're doing this, right? Forget. I'm reminding you. All right. So things to write down. One thing that we were working on maybe is how to study. This is great. Watching this is and interacting with me is great way to study. Helpful thing is hopefully you've got like just a scratch piece of paper, a pad of paper, whatever, something to just write down little tidbits that I'm talking about. Maybe even like go like unit 1, and then it's like you could write down little tips for unit 1. And if you haven't, maybe you go back later and jot this stuff down. Velocity is slope for a position time graph, also known as a distance time graph. All right, or a position. I'll write the word graph. All right. So velocity, that's a O. Velocity is slope for a position time graph, distance time graph. All right, that's key thing right there. So in a position or distance time graph, how do you find the speed of an object? Were you paying attention? I hope so, because all you got to do is rewind 10 seconds and I will have given you the answer. So you all know it. These are other options to find maybe other things, but to find slope, or to find speed of a distance time graph, you find the slope. Oh yeah. This letter C is something. It's okay. I believe you. This is gonna be like something later. It has nothing to do with this. I will say this. This is not for a graph. The equations are for when you just have variables and numbers. If you've got a graph, it's almost like a slightly different set of tools to use to analyze graphs. And so we get this equation from the graph that we can use for when we don't have a graph. And I'm not even saying this won't work, but specifically for a graph, probably the best way to get the information, because I mean, think about it this way. If you're using this, you've got basically one number for distance and one number for time. Maybe 2, because you maybe found the change. For a graph, you hopefully got like 17 of those, to help you out. And so more numbers means less variability and less error. So bottom line is for a graph, find slope to find speed. Okay. All right. A car accelerates at 6.2 meters per second squared over the course of 100 meters. What equation would we use to figure out how fast it needs to be going at the start if it needs to get up to 44.5 or 44.3 meters per second by the end? Okay. How do we figure this out? I don't know. I wasn't there. How I mentioned this. I don't know how much Mr. Kelly I don't know, communicated how important the 4 steps is. I think I did it when I got back, but that's what I want to communicate here. You've got all these equations to choose from. I mean, if you got the equation sheet in front of you, it basically looks like this, except in a slightly different format. How do you even begin to choose? I'm sure most of you know how to do this, but I want to remind you how to do it anyway. You start with what you list the variables. You start with what you know. When you've got meters per second squared, hopefully you did the review guide or you started it, and this is an acceleration. All right, whenever you see a distance over a distance squared, distance over a time squared, or a distance over a time, it's the same thing. Like it's the same as meters per second. That's also acceleration. Why is that? Because if you think about it this way, meters per second is basically meters over 1 times 1 over a second times 1 over a second. And when you combine all those together, you can either write, well, like if you combine the meters and the seconds and then you divide it by seconds again, that's basically what is going on there. That's the top, and then this becomes the bottom. Or if you just multiply across, you get meters per second squared. It's the same. That's why they're both the same thing, if you ever wanted to know that. Probably didn't need to spend 30 seconds explaining that in this review guide, but anyway, that's an acceleration. So I'm going to write that down. I'm going to write A equals acceleration is 6.2. I'm not going to solve this, but I'm going to set it up so you can figure out how to solve it. 100 meters. Well, that's a distance. That's a displacement. So displacement equals 100 meters. You keep going. Okay, what equation? We figure out how fast it needs to be going at the start. So that's VI, the initial velocity, is going to be our question mark. If it needs to get up to 44.3 meters per second by the end, that's meters per second is just a velocity, right? That's just a distance over a time. So by the end, that's going to be VF, 44.3 meters per second. And that right there is enough information to figure out which equation to use. Because now we go through, it's like, well, we don't have V average. We have an initial and a final. We can't even figure out V average. Well, maybe we can. Just divide by 2. I bet that would work. But let's not make extra work for ourselves. That might work, actually. But oh, wait, no, because we got acceleration. We don't have acceleration listed here. We also don't have time. So we can't use that because we don't have time. We do have distance. VF, okay, that's what we're trying to find. Maybe this is it. Ooh, we have A, T, wait, we don't have time. So we can't use that one. All right, distance, okay, we've got that. Oh, there's time again, so we don't have time. Ooh, that's the correct answer. All right, see what I'm doing here? I listed, sorry, with that cold. I listed the variables and I'm going through and I'm eliminating it. Here's D again, which we got, but here's time again. So it can't be this one. It can't be this one. So it's gotta be that one. That's the only one that works. We're trying to find VF. We have VI, we know acceleration, and we know distance. So there we go. That's how you choose what equation to use. So what I would do is I would write down VF squared equals VI squared. Plus 2AD, and I would go from there. I get like in the 2 years ago, last year even, I think everyone was being taught to rearrange this ahead of time. I think it seems like this year you're being taught in your math class to plug in the numbers and then rearrange, whatever works for you. So, but this right here is basically the end of the physics, and now you would plug in the numbers and solve for the missing variable, and that's algebra. So that's what you would do. I'm not going to solve it because, you know, we've got many other things to talk about. If you want me to, I can later, but not right now. All right, but that's how you set it up. All right. Now, this one looks suspiciously like it might be from Unit 3, but it's not, because, I mean, it is, but we're going to come back to this in Unit 3. It's a really quick question. What is the acceleration and gravity of the ball on the ball at the top of its path? Ooh. All right. Don't let this trick you. It's asking for acceleration. Yeah, it is B. All right. So that's it. It's always gravity. Gravity is always pulling it down. Every single time, gravity is pulling it down. All right. So. In fact, we have that letter for it. Gravity, 9.8 meters per second squared. And if we get into Unit 3, when we start talking in direction is important, then yes, we would put a negative in front of that to indicate the direction. We could do it now, but we're not getting into that. It's definitely not like you're like, oh, there's a negative sign right there. That's like, okay, wait, slow down. Negative sign, but it's like that's a velocity. It literally says V for velocity, so don't let that fool you. It's always 9.8. Always 9.8. I'll just leave it at that. Okay. Motion graphs. Everybody's favorite topic. This is about the time you started questioning whether you should be in honors physics or not. When we started talking about the motion graphs. I'm sorry I wasn't there. It wouldn't have made it any better because it's hard to learn. So we got 4 motion graphs. These are velocity time graphs, so they're a little bit different than we just looked at a few minutes ago, 20 minutes ago. Which of these shows objects? Which graph shows objects that are moving in the positive direction? It's okay, and slowing down. There are 2 of them, so good to go. All right. Motion graphs in general will tell you 2 things. They will tell you you want to approach these things slowly. You want to approach these things. We're tempted to just like get through it. Like, okay, I got, what is this doing? Okay, what is it? But just take like half a second and remember, look for 2 things, 2-part problems every single time, 2-part problems. You got to ask yourself these questions. Ask yourself. My handwriting is bad enough. I'm writing on a trackpad, so I apologize. Ask yourself, what is going on? What direction is it going? Direction. All right. What direction is it going? And for the previous question, several slides ago, it was the slope. If it was sloped downward, it's moving in the negative direction. If it's sloped upward, it's moving in the positive direction. Those were position time graphs because position means velocity in those. I'm sorry, slope means velocity for a position time graph. For a velocity time graph, the graph tells you velocity. And in these cases, you just got to look at the quadrant. And so this first one, it's positive. It literally says it's a velocity time graph. Hey, there's a positive little plus sign right there. That means that letter A is a candidate because it's moving in the positive direction, which is what we want, positive direction. Choice B is not a candidate because all the velocities are in the negative quadrant. So no matter what the slope of the line is doing, it's all in the negative quadrant, which means it's always moving negative. C, it's a candidate because they're all moving, the velocities are all in the positive quadrant. D is a candidate because they're all in the positive quadrant. Okay, so all 3 of those are moving in the positive direction because their velocities are positive at all times. And the other one is what is happening to velocity? What is is velocity changing? Is it constant? Is it changing? Is it changing going faster or is it changing going slower? Let me summarize that. The 3 choices are these. No change, constant, in other words, no change, no, I don't like what I was about to write there. I'll simplify it. Speeding up. And your other choice is slowing down. Okay, those are your 3 options. That's it. That's the only 3 options there are. And no change is in a velocity time graph. In a velocity time graph, no change would be a flat horizontal line because it's basically sitting at some number. Okay, so this is no change. I don't like this. I'm not going to use that. I'm just going to just verbally say it. Speeding up is tricky. I can't draw it actually. I'm just going to point it out. Speeding up means the number is getting farther away from 0. Slowing down means it's getting closer to 0. 0 velocity. Okay, 0 velocity. We want to know which one is slowing down, which means it's going to be getting closer to 0 velocity. A is getting closer to 0. It starts out high up, not 0. And as time goes on, it gets closer to 0. All right, A is an answer. C is also a winner because same thing. It starts out at some non-zero number going positive and it ends up near 0 or at 0. D is not a winner because it starts out at 0, not moving, 0 velocity, and it ends up speeding up, getting farther away from 0. Okay. D, or this one over here, the one we already eliminated. Yep, together you got it. B is slowing down as well because it's starting out at some non-zero number. So I'm going to write slowing. Fasting, that's not the right word. Let's just say speeding up. And this is slowing. Okay, so well, I hope that helps a little bit. That's what you want to do. You look for the direction in a velocity time graph. Good. In a velocity time graph, you could quickly tell, is it moving forward or backwards, positive or negative, we'll say. And all you got to do is look at the quadrant for that. Quadrant. If I say any other word while I'm spelling this out, I'm going to spell it wrong. So the quadrant, I'll put a little question mark after that. What quadrant is it in? Positive or negative? That's it. So I'll just like write or zoom. That's your options. Positive or negative quadrant. Okay, is it going backwards or forward? Positive or negative? And then is it speeding up, slowing down, or not changing? Getting closer to 0 would be slowing down. Getting farther from 0 would be speeding up. And a horizontal line is just maintaining that speed, not changing. Okay. All right. Now, makes sense now. Hopefully you remember it. All right, now you can do this. Same 4 graphs, even if you just paid attention the last 5 minutes. But maybe you could figure this out if you didn't listen or you forgot. Which ones are getting faster? Which one or which ones are getting faster? It doesn't matter if it's going positive or negative. It didn't ask that. So getting faster for a velocity time graph is where the velocity is getting farther from 0. So it is not A because it's getting closer to 0. It's okay. It's okay. See? So good. Oh, so second guess your answers then. All right. So you're learning that. So it is not, that's getting closer to 0. It's getting slower. This is getting great. To answer your quick question, no, there are no FRQs at all. It is 75 multiple choice questions. All right. So D is the only answer. Getting farther from 0. That's it. Farther from 0. Okay. Yep. I feel like I just asked this question. Getting faster. All right. I feel like this is a, well, whatever. Hopefully you're an expert by this. I don't know why they put this one in here. I tried to eliminate it. All right. Getting faster is getting farther from 0. It's a velocity. Double check. Is it a velocity time graph? Yes, it is. So velocity time graph. Be scared. It'll be okay. I know. You'll be fine. It'll be okay. You're paying it. You're taking a good step by watching this, so it's good. Just pay attention, right? Ask me questions. So farther from 0, faster, getting farther from 0 in a velocity time graph. Velocity time graph. Okay. Faster. Well, we'll talk maybe about that in a minute. All right, which one's changing directions? Oh, what? Speaking of changing directions, I'm not really though, because remember there's 2 things that you can learn from a velocity time graph. Is the first thing I said was what direction is it going? Right? You might be tempted to say C, and that is not correct. It looks like it's changing directions, but man, we got to like train our brain to remember that these lines aren't the object. These lines are not like a visual of the object moving, you know. It's not like it's not like a time lapse of, oh, the object is like bouncing off that. That's not what's going on. These lines are representing the velocity, which is something that is kind of an abstract concept anyway. You cannot see velocity. So we're trying to make a graphic representation of velocity. And but our brain is like, no, this is what it's doing. Like, but it's like, no, shh, brain. Okay, so this is not, these are always positive. The whole entire time for letter D, it is moving forward, positive direction. But what happens is it slows down at first, stops for an instant, and then speeds up, still going in the same direction. All right, that's all it is. Same thing with this one, kind of. I mean, that's obviously not it. Yeah, this one changes direction. You already answered that. Why? Because at first it's moving in the positive direction. It slows down, and then it's like in a car. You slow down going forward, and then you speed up going backwards. That's that. Okay. Changing direction for a velocity time graph. Yeah. All right. Now, I am 98% sure. You're like, well, what about a position time graph? I'm 98% sure, and if I'm wrong, I'm wrong, and I will make things right for that. Pretty sure you're not going to see those curvy graphs for position time graphs. Okay. This thing right here is slowing down, if you're curious, because it starts out with a steep slope, which means a high speed. High slope means high speed, and it ends up with a shallow slope, which means a low slope or a low speed. Pretty sure we're not going to see any of those. Pretty sure. There's other questions I could tell you later on. I'm absolutely sure there's not on the test, but you don't have to worry about those. Okay. So be able to know the parts of an experiment: independent variable, dependent variable, constants. Several of you had trouble with that on the lab practical thing. Just make sure you understand what constants are. Independent variable is what you're changing. Dependent variable is what's changing because of that. Constants are things that could potentially change, but you're making sure that they don't. That's what constants are. They're, identify and solve for any variable in the kinematics equations. Okay. So in other words, there we go. So when you see the equation sheet, these things basically, you've done this, you've done this. So yeah, right. I know you were scared. Don't be scared. Yeah, that I'm telling you, it's a 75 question multiple choice test. There's only so much we could cram into a test. And I'm trying to tell you, if you're paying attention today, right now, watching this, that is a big clue about what's not on the test. Okay. So I'll be more direct about some other things later. There are no catch-up questions. There's no questions about like if so-and-so leaves going 5 meters per second and then 10 seconds later the other person chases after them going 7 meters per second. When do they catch up? No, none of that. Right? So it's, yeah, if you understood what I just said in the last 38 minutes, you're good for Unit 1. Okay? But make sure that I can't do everything right now. But look at the review guide, make sure you're pretty okay with the as good as you can get. Don't spend so much time on the distance graphs and whatever that you forget everything else. Any math on the test. Yeah, there'll be some math. You'll have to solve for some variables. You'll have to solve for some variables. Okay. But they'll be somewhat simpler. They'll be the simpler ones, the ones that don't take 20 minutes to solve. Okay. As long as you can identify the variable, rearrange the equation to solve for it, you'll be fine. It's sort of like what I started like a little bit ago, those kinds of questions. All right, Unit 2, law of inertia. You probably know it. Just read them. Make sure. A good thing on the test is if one of them doesn't make sense, it can't be all of them, right? So, but if you All right, you're right. B is good. That's like the one that everybody knows. D is also true. Yep. D is also true. C is also true. A is true. A is true. All of them. That's law of inertia. Okay. All of them. Told you. I don't like definitions because definitions are very limiting. But this is one of those concepts. There's a few of these concepts where the more you learn about the concept, the less helpful a strict definition is. Okay. This is one of those. So make sure you understand the concept and don't just memorize a definition for inertia. Okay. Well, to answer that question, like Jai, is like, don't forget, I'm not asking them the same. I'm not asking these questions the same way as you'll see it on the test. Okay, I'm asking this. A lot of these questions I ask in a way I formatted them to kind of help with discussion about the questions and the concepts and whatever, and the underlying principles. So I think it'll be a lot more evident. Like there's no like, I think I know. Okay, I know what you're asking. I think I know what you're asking. There's no like check boxes. You know what I mean? There's no like 4 choices and you check the boxes of, you know, choose however many you think are correct. There's none of those. It'll be like a standard old fashioned, like, yeah, yeah, like it's like your choices are A, B, C, and D will be like all of the above type. Those are the kinds of questions we're looking at here. All right. So like if you see something like this, I'm not saying the question is gonna be formatted like this, you know, but yeah, I think I understand what you're asking. I think, okay. All right, which has more inertia, a bowling ball at rest or a small marble rolling across the table? Why? Okay, now there's no way to answer why on this except through the chat. But make sure you know the answer. More inertia. Yes, you got it. Why? Because mass. Okay, inertia, mass is equal to inertia. This is, in fact, if I was to be a little bit more descriptive with how we talk about inertia and mass, I would say inertial mass. That's how we define mass. All the mass we've been talking about so far this semester has been no, half of the time we've been talking about inertial mass. It's not a distinction you need to worry about, but it's basically mass is inertia. The more mass something has, the more inertia. Not to be confused with momentum. All right, momentum later we learned is something related, but it also involves velocity, and that's not it. Inertia is only mass. Yep, good. Constant velocity. All right, you can be sure that these types of questions similar that you would have seen on the physics class. Mine's on physics, you know. If it's moving at a constant velocity, there's only one thing you can be sure of: that there is no net force. In other words, the forces are balanced. You remember this? If you have balanced forces, good. Yeah, you got in with the, you know, before the delay hit, so you answered before I answered. If you have any net force, it's going to accelerate. Okay, if you have any net force, this is Newton's second law. If you have any net force, any unbalanced force, it's going to accelerate in the direction of that net force. Okay. Just using the word net force, this sentence is like nonsense. Okay. Any net forces are canceled out. That doesn't even make sense. All right. Because if it's canceled out, there's no net force. If there's a net force, it's not canceled out. Like the definition of a net force is the leftover forces after everything else has been canceled out. So this doesn't even, like, this is like garbage. Okay. And yeah, you can be sure that if you got constant velocity, you have balanced forces. They cancel out. Okay. That is like the principle of Newton's second law. Acceleration causes A net force causes an acceleration. Net force causes an acceleration. If there's no net force, there will be no acceleration. That's Newton's second law. That's like a law. All right, there's not a lot of laws in physics. So if there's a net force, there's an acceleration. If there's no net force, if they're all balanced, there is no acceleration. If an object is moving at a constant velocity, wait a minute, did I just, hey, look at me. All right, well, hey, emphasis on the constant. Man, somebody needs to check his work before he goes like live on YouTube. All right, when you throw a ball, why does it keep moving once it leaves your hand? This is one of those things where you think you understand inertia, but this really checks to see if you understand inertia, the concept behind it, not just the definition. The answer here, yeah, the answer here is C. Okay. If I instead of using the word mass, I use inertia. There you go. Why does it keep moving once it leaves you? Okay, exactly. Why does it keep moving once it leaves your hands? You're no longer pushing on it. Okay, so it's not D. Same. A and D are the same, saying the same thing. The only reason it keeps moving is because it's moving. All right, it doesn't remember anything. It's like, huh, what? So that's it. It has mass. It has inertia. That's all I can say. There is no, just remember, if it's in the air, you throw a ball, once it leaves your hands, it's out of your control, literally. You can't do anything. You're not doing anything to it. Gravity is affecting it, and that's it. I mean, air resistance, but we don't, we ignore air resistance. Hey, we remember these, right? These are amazing, right? Which of these represents the forces acting on a car moving at a constant speed? What's the key word here? The key word here, I mean, it's moving. Okay, that's not the key word. Okay. The key word is constant. The key word is constant. Whenever you see the word constant and you've got these little arrowy thingies, okay, you got to think balanced. Whoa, not balanced. I could spell. You got to think this is balanced. Okay, whenever you see the word constant and you're talking about forces, look for balanced equations. A is not a car. This might be a spaceship where there's no gravity, no forces acting on it, but it's a car. So we're on Earth, so it can't be A. It's not B, because it's not balanced. C's not balanced, D's not balanced, E's not balanced, F's not balanced, G's not balanced. Ooh, H. We'll come back to that. I's not balanced, J is balanced. So, okay. A is A, I. All right, Griselda, you chose, well, yeah, I don't think you're Griselda, but you chose mostly, you guys got it. You got this. All right, you got this. A is not feasible for a car, so we're going to ignore that one. But it's balanced. Technically, it could be a choice, but it's a car, so we're going to ignore that one. H is basically if there's no friction. If we're ignoring friction, then you've got basically the force of gravity pulling it down, and you've got the normal force pushing it up, the normal force being the force of the street, the force perpendicular to a surface. Okay. If we're talking slightly more realistically, you still have the normal force and you have the gravity pulling it down. And then one of these is going to be friction and the other one is going to be the force applied by the motor. Okay, balanced. It doesn't even matter. It could be like people pushing the car down the street because it got like stalled out and somebody has to push it and like, there's tree branches in the way. It doesn't matter. The forces, whatever forces are there, they're balanced. And that's the big takeaway. If you see the word constant and you're dealing with these like force diagrams, then you got to look for the ones that are balanced. Okay, constant speed. I'll just include that. Constant speed, because that's kind of the point. Which of these represents the forces acting on a book that slides to a stop while moving toward the left? Now be very, very careful with this one. Okay. How do I put this? In the force diagrams, arrows are not the velocity. So one of those things, again, you have to remind your brain that these are not pointing in the direction, necessarily pointing in the direction that the object is moving. All right. So if we're talking about something sliding to a stop while moving toward the left, what do these arrows represent? They represent forces. Okay. So we're going to have to find, in this case, one of these things that represents maybe gravity, normal force, and then what is causing it to slide to a stop. I'm seeing a lot of choices here. None of them are actually correct. It's not I. Not I. That's the one where it seems to make sense. Okay. And you chose it. Why did you choose it though? This one looks like it's sliding to the left because the arrow on the left is bigger. But if that was the case and these arrows represent forces and you're pushing harder to the left with a greater force, which is what that larger arrow is showing, that means that the book would be speeding up to the left because you're pushing harder in that direction. Okay. These arrows represent pushes and pulls. If you're pushing and pulling harder to the left, it's going to speed up to the left. So it's already moving to the left. Remember this question? It's already moving to the left. You don't need to push it to the left. It would be air resistance, but even more would be probably friction. Yeah, air resistance and friction. Okay. If you see the word sliding, sliding represents, that's like our way of saying there's friction involved. Okay, just the rubbing of two surfaces together. So let's look at all of these. Now, let's just look at the correct answer. The correct answer is D. Let's talk about why. All right. These ones are the most obvious. Here's your when you remembered how to do this. You got your force of gravity pulling down, you've got your normal force pushing up. Those are the clear ones. This okay. So what's going on here? Well, I will just, maybe if I do this, that is the force of friction pushing it to the right. The book is already moving. According to the question, we're looking at this question as after it's already started. All right. We don't have any information about why it's moving to the left or who pushed it or what's going on. We just know that the book is moving to the left and it's sliding to a stop. So it's we don't need something to push it to the left because it's already doing that. Remember inertia. But something is causing it to slide to a stop, and in order to cause something to stop, if it's being pushed, if it's sliding to the left, we need something pushing it to the right in order to stop it. That's what makes this so confusing, because once again, these arrows represent something that's not really like visible. It's representing something that we're not quite used to representing and seeing. We're just used to like having it already there and built into everything happening. So these are force diagrams. That's all I could, so these represent forces. Yes, those, you're correct. Those are good. Those are appropriate reactions to these questions. Which of these represents the forces acting on an egg falling at a constant velocity? Incidentally, please ask questions. I'll go back gladly. If your brain is processing what I said, I will gladly answer these. Which of these represent forces acting on Constant velocity. Constant velocity. Yeah. Remember, the constant means balanced, right? Constant means balanced. Constant means balanced, 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 balanced. So the answer has to be H. All right. H. Balanced. Balanced. Falling through the air. There's nothing pushing it side to side. Balance forces. This is going to go longer than an hour, I'm starting to think. A box is pushed with 5 newtons to the north, 12 newtons to the east. And there's 2 newtons of friction to the south and 3 newtons of friction to the west. What is the net force? What? Well, what's going to help is to draw a visual. Assuming there's not already a visual there. So we got 5 newtons to the north. All right. One thing that hopefully it'll be on the, maybe it won't be. I'll draw it on the board. Is the never eat soggy waffles. The compass. All right. I'll make sure that's there for us. So in the end, it's not going to necessarily matter, but for us, for today, let's just make sure we got this. So this says 12 newtons to the east. So there's 2 newtons of friction to the south. So, whoa. 2. And 3 newtons of friction to the west. So that's this direction. All right, what do we do? Basic steps here, like first add what you could add. All right. There's nothing to add. I mean, unless you count what I'm about to say next. These two are basically the same thing, subtract. So add and subtract first. Ones that are on the same side you'd add, ones that are on the opposite side you subtract. So what ends up happening is you end up with 12 to the east, 3 to the west. So you're going to end up with a box that looks basically like this. All right. Because 12 minus 3 is 9, I think. Yes. And then you got 5 newtons to the north, 2 to the south. So you're going to end up with, my arrows are no longer to scale, but they never really were. With that, add and subtract. That's the first thing you want to do. You just sort of simplify things. And now, hey, look, this is very reminiscent of a triangle where you're just trying to find the third side. So this is a 3-9 triangle, which I don't even know if that's a thing. But your third step in these cases would be the Pythagorean theorem, a squared plus b squared equals c squared. And so in this case, it would be 3 squared plus 9 squared gets me that answer. And I'm going to do the little trick. Most of you probably know about it, but I don't have to rewrite that. There's a little button. Usually it's down here in the bottom of your calculator. It says ants. All right, it might not look exactly like this one, but it's basically that. And since ants, that stands for answer. So since answer is in yellow, I gotta push my little yellow button, and I just hit ants. And well, I did it too early though. I need to take the square root of my answer. So take the square root of my answer. Yeah. So 9.4 to the northeast. It's going to be a combination. This doesn't quite do it like that. That's not really how you would draw it. You wouldn't draw it like this. You would probably draw it like north and then east. So like 3. You always draw tip to tail. You don't draw like tail to tail. You don't do it like that. You draw tip to tail, and so it'd be 9 one way. And then this is really what it would look like. All right. So northeast. So yes, it would be A. All right. Add, subtract, Pythagorean theorem. Well, what about SOHCAHTOA and all that? Yeah, what about that? Strange that I didn't mention it tonight. All right. Got that? None of that on this test for these forces. So no resolving the vectors and all that. At least not like this. No, we're tested on that. So what does an unbalanced force cause or do? What does an unbalanced force do in this case? It's already unbalanced. It's already unbalanced. So if it's large enough, it doesn't matter. It doesn't matter the magnitude or the size of it. It doesn't matter. If it's unbalanced, it will always, 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 always cause an acceleration. Once again, it's a law. And I know we were taught, be careful when a test question says always or never. And that's a valid strategy when you're taking a test. But when we're talking about a law, Newton's laws, that is always. All right. All right. Always causes an acceleration. Always. Second law. All right. Let's put that there. Second law. No questions, no exceptions. Hey, no, always. All right. You don't have to preface. Yeah, what's your question? I'm paying attention, but I'm also going to read this while you're writing. What is the reaction force to the black dog pulling on the rope? Ooh. Okay. Yeah, there's a test where we need to find displacement on the graph. Ooh. I'm gonna say a definite maybe to that one. Will we need to find displacement on the graph? I don't remember if that's not the case. Ooh. Ask me again in class. Because I don't want to pull up the test on, the internet, live on the internet, and have everybody see test questions, because that would be sort of irresponsible of me. I don't know. I don't know if there's, okay, but I don't know. If you find displacement on a velocity time graph, you find the area under the line. That's the one you're talking about. I believe I have it on the review guide. I think. I gotta get back to you on that one. Okay, so back to this question. That's a great question about the air displacement. So what's the trick here? I don't know. I don't remember what I talked to you about this. The reaction force. So for every, this is like one of those things like we could just recite it and not even like think about what it means. For every action, there's an equal and opposite reaction. It's like, I mean, somebody who's in 5th grade would probably say that. And again, it's like we say the words and it's like, okay, we got it right. Yay, we move on to that. But what does it mean? This is one of those things where the definition kind of almost hurts us in some ways in our understanding and application of it. The trick for this, whenever you see like a question asking about the reaction force or the action to reaction forces, like whenever you say for every reaction force is an equal and opposite reaction force, here's the trick. And I think I've said this, but I don't remember. I'm going to say it again anyway. The trick is this. This is my asterisk. Holy cow. That's okay. Well, whatever. Is that better? I don't know. Switch. It's getting late. Switch the nouns. It's a terrible. Switch the nouns. That's the trick for figuring out reaction and action forces. Literally, black dog pulling on the rope. Rope and the directions. Okay, so and direction, I guess. I'll add that. Direction. But switching the nouns is like the big thing. If black dog pulls on rope, rope pulls on black dog. So you're right, it's C. That's it. Switch the nouns. You're like, but what about the white dog? Yeah, what about the white dog? It doesn't matter. That rope could be attached to a wall, and it doesn't matter. The dog is pulling on the rope. The dog is not pulling on the other dog. The dog is pulling on the rope, and the rope pulls back on the dog. Okay? Switch the nouns and the direction, and you're good. All right. Small car going 20 meters per second collides with a large truck that's at rest. Which one experiences the larger force? Why is this under Newton's laws? Oh, wait. So we're talking about Newton's third law. For every action, there's an equal and opposite reaction force. Right. The answer is neither. It's the same force. Different, like, effects. I mean, if you go up to a truck and swat the truck, it's not going to have any effect on it. But if you go up to a bug and swat the bug, it's going to like kill it. So the force is the same. The force is the same, but the effects of it are going to be different. Yeah, see. All right. So we'll be able to solve for any the variables in that force box. That's this box right here. Where'd it go? There it is. Any of these, except for this one. Don't worry about this one. Just this one. We didn't talk about that. So any of these though, make sure you can solve for. All right. Well, specifically these two. F net. The first one is just a reminder that F net is just a total. So specifically, make sure you can solve for those three variables. All right. And will there be vectors on the test? No. I mean, how do I put this? Let me vectors on the test. Not just pure vectors, arrows, solving for no, none of that. I think I know what you're asking. There won't be any of that resolve this vector, into its components and all that stuff like that. No, I mean vectors are on the test because all these things are vectors. But I think I know what you're asking. Is it well, what about this? Do we have to do this, and we have to do Vy and Vx, and we got to do the SOHCAHTOA, we got to do the hypotenuse and the opposite and the adjacent. No, that's not on the test. You've already been tested on that stuff. This is a final test that's meant to be quick. All right, identify any forces and the arrows that represent them. So make sure you're familiar with normal force and friction force and tension and all those. Know the difference between mass and weight. Okay, mass is m. Weight is the force of gravity, literally pulling you down or pulling the objects down. Fg equals mg. That's what I was talking about earlier. I showed you Fg equals mg. G is 9.8. All right. Know that when two objects apply, the force is always the same. Okay, so that's I just got done, and I'm bringing that up again because it's gonna come up. All right. If you got questions, put them in there. I'm not seeing anything coming up on Remind lately, so we're good. All right, Unit 3, 2D motion. You're going to be happy about this one. Which will hit the ground first? A ball thrown horizontally really hard out the window, 16 meters up, or a ball just dropped from that same window? Which one's going to hit first? Yeah, good. They're going to hit at the same time. Why? Because if a ball is just dropped to the ground, or another ball is right behind that, thrown horizontally, the force of gravity pulling them is the same. Gravity is pulling that, or accelerating. They're both accelerating at negative 9.8. So it's not Fg. I'll just put G, I guess. But they're both accelerating at 9.8 negative. Toward the ground. So they're both going to have negative 9.8 meters per second squared. The horizontal velocity does not affect the vertical velocity, and vice versa. Great. Oh, hey, look, I forgot I have a picture. It was a weird weekend. So yeah, doesn't matter. All right. Hey, look, a question from the review guide, number 99. Number 99. Lynette rolls a steel ball horizontally at 2.3 meters per second from the ground of a platform that is 2.5 meters. Where did it hit the ground? All right. I want to do a quick summary about how to do this. It's going to be kind of quick. So, if you got questions, let me know. I like to draw a diagram to start with. This one I had a time. Good. Well, good. I'm glad I'm going to do this then. Maybe I won't go as quick as I won't fly through it. So it hits the ground over here. Okay. Remind yourself. I just draw this to remind myself that this is the dy, the distance it falls in the vertical direction. And then how far it goes along the ground, the range, is going to be your dx. And there's a little trick to remember for your dy that I'm going to have to remind you of. And the fact of it is, I'm going to remind you of it now, I'll remind you of it later, it falls down. It starts at like 2 point, so it starts at 2.05 and it ends at 0. And that's important to remember, and I'll tell you why in a second. So what I recommend you do is list all the variables. All right, just go down that list. Remember this, D, V, A for the X's. Okay, now you may have advanced a little bit more in math from when we first did this, when you first did this with Mr. Kelly. But if you're not sure, go back to the basics and just do this. Okay, and then you do the same thing for the Y's, D, V, Y, A, Y, and then, you know, all these are going to equal something. You're going to try to identify all of these. And there's a couple things to remember. First, the things that are always true. And I'm going to put my little crazy asterisk by those. Okay. AX for something that's for a projectile is always 0 because there's no acceleration in the X direction. There's nothing accelerating it this direction. All right. If it's going sideways, it's going to continue to go that speed. Ignoring air resistance. And yep, AY is negative 9.8 meters per second squared. And now we got to start, when in doubt, use negative, okay, for 9.8. In this case, it's very important because gravity is definitely pulling down. So AY, that's going to be our negative 9.8, okay, always for a projectile. Then you gotta like do a little, wait a minute, okay, Vy, this is gonna be your initial, because acceleration in the X direction is 0, Vx is just gonna be your average velocity. This is gonna be, I mean, we could even put this if you want to, but it's implied. That's gonna be our average velocity. Vy, because we have an acceleration, is gonna be our initial velocity. In this case, it's horizontal. We'll get there in a minute. Let's go down our list. Dx. Well, that's what we're trying to find. All right. Where did it hit the ground? That's dx. Where? How far away? Great. Yeah, this will go quick. We're almost done here, actually. Vx. Well, it says 2.3 meters per second thrown horizontally. Okay. Dy. Dy is the height. Now this is sort of important. I told you it goes from 2.05 down to 0, which means it's going to be a negative 2.05 meters. You'll have like a big warning sign if you don't remember that. So your calculator is going to yell at you later. VIY is 0. Okay. It just rolled off the table. So the VY initial is 0. They're not, she just rolled it off. Okay, it's rolled off. It wasn't thrown. All right. First thing you gotta do, find time. Find time. All right. To find time, use either X's or Y's, not both. You cannot mix these together. You cannot mix these together. And to find time, use whichever you have more information for. We are not going to use X's because that's where our question mark is. So we're going to have to use, we're going to use the Y's because that's where we have all our information. And you look at your equation sheet, and there's that one equation. There it is. It's this last one right here. If Vi is equal to 0, we can use this equation. And that's going to be a safe bet to use for this, for finding time in general for these. So T is equal to the square root of 2 times D. And this is how it's written over A. And to remind you not to mix up X's and Y's, it's a good idea to just throw in those little Y's just to remind you when you're putting in numbers later. All right. If V, Y is 0, it is. So I'm going to plug this in. 2 times the distance that it falls, so negative 2.05 meters divided by negative 9.8 meters per second squared. And here's where you'd get that little warning. If you tried to plug it, if you tried to take these two negatives are going to cancel each other out. These two negatives are going to cancel each other out. If you only had one of the negatives, you would end up with a negative number, and your calculator doesn't like taking square roots of negative numbers, so you would get yelled at right there, and that would be like a big clue that you did something wrong. So 2 times negative 2.05 divided by, I'm going to do this little piecemeal here, negative 9.8. Get that, and now I need to take the square root of my answer, second square root of my answer, and so I get time is 0.6468 seconds. What ends up happening is the meters cancel out and the seconds is squared here, and it gets unsquared when you take the square root. That's how I get seconds. All right. So that's the first thing you do, find time, number 1. Then use like in this case, we now have time, we have D, and we have V. Really only one equation is going to be helpful there. It's the V equal V average is distance over time. And so at this point, you could tune me out for a moment if you want, because I'll tell you why in a minute, but I'm going to explain it anyway. Now I like to rearrange things before you plug in the numbers, but we like, I guess this is how we're being taught now, so I'll roll with that. Distance is our question mark. You can put it whatever you want there. Time is point. Why did I round it to here? I don't know. I put a bunch of numbers. I try not to round too much until the very end. That's basically what I do. Then I lost my cursor. Where am I at? Oh, am I on the right? There I am. Then I gotta get D by itself, so I'm gonna multiply times 0.06468 seconds, which will cancel. That's a multiply. Did I do it wrong? Oh, that equation would work as well. I'll tell you why in a second. I think it would. Yeah, that would work as well. Great observation. Let me finish this one up and I'll show you why that would work as well. And then I just multiply that also times 0.06468 seconds. Seconds on the bottom here, cancels out with there. And I end up, where did I get 2.2? Where did I get 2.2? Oh, jeez. It's 2.3. Thank you. This is why you write stuff down. See, you catch little problems you make. 2.3 meters per second. I got that VX. So great. That's a great catch. So I'll take my previous answer from before, multiply by 2.3. And my final answer is 1 point. Now I'm going to round to the tenths, I guess. And it's at meters is distance. So there we go. That would be my final answer, 1.5 meters. Now, somebody said, I thought it was this equation. Mr. Zorn just asked me how do I bring up my Pip-Boy in Skyrim. Mr. Zorn is a chemistry teacher, if you don't know that. And he knows I have over 1,000 hours in Skyrim. Anyway, to answer this question, what about this equation? 1/2 AT squared plus V. Yep, VI. He likes Fallout. I like Skyrim. It's all good. I prefer Skyrim. What about that equation? Why wouldn't that work? It would work. Watch this. I could just plug in my number. Equals D, because that's what we're trying to find, right? Why not use this equation? Well, 1/2 A is 0. That's great. So it doesn't even matter what our time is. Holy cow, 5,000 hours. Times the time, 0.6. It doesn't even matter, 6468, because it's going to be 0 plus VI, which is 2.3 meters per second, times the time. And we're basically doing the same exact thing we just did up above. So this equation works. That's the nice thing about math. Math works. So, uh-oh, did I do the equation wrong? Very possible. Look at my calculator. 1.49. I did get 1.49 when I originally did it. 1.38. Oh, you know why? Okay. No, you're close enough. What happened is we have rounding differences. That's basically what. So if I do 2.3, it's gonna be the same exact thing. 2.3 times 0.6468. Yeah, see, I rounded it a little bit differently and I got a slightly different answer. Most likely you rounded something, or maybe you put a number in the calculator differently than you should have. Yeah, I rounded to 0.6. That's why. It's just rounding differences. That's why I say try not to round too much until the very end, because every time you round during a problem, you're introducing a lot of error. And the more you round, the more error. I mean, you're making it less like precise. So every time you take away some precision, you get farther and farther from the most precise answer at the end. So try to round as little as possible throughout, and then at the very end, round. All right. So anyway, that's how you get it. And so both equations would work. It's great. Math is wonderful. So this either equation works. Now, here's the good news. You don't have to worry about any of that. I'm just going to tell you, all you need for the final is to find time. I'll say that one more time, and then I'm going to move on. For these questions like this, all you need to do is find time. There's no other calculations about projectile motion on the entire final. But if a ball is thrown upward, it has an initial acceleration of g, gravity, and an initial vertical velocity of 21 meters per second. What is the acceleration at the top of the path if it climbs to 10 meters? Now, yeah, don't let it fool you. It's got a lot of information on there, but the only information you need is what is the acceleration at the top of the path. It doesn't even matter. Anywhere along the path, gravity pulls it down. That's all you need to know. Acceleration is gravity. Acceleration is gravity, and it's always in effect. You are sitting near the center of a merry-go-round, and your friend is sitting near the edge. Who has greater rotational speed? All right, so rotational speed. So you're A, your friend is B. Rotational speed is just the speed at which you go around, how many times you go around per second. And the answer is C in this case. Yes, the answer in this case is C. You're both going to go around the same number of times per second. All right, that's all there is to it. You're both going to go around the same. You're attached. You're on the same merry-go-round. Okay, that's rotational speed. It's just how fast do you go around? The RPMs, rotations per minutes. That's all it is. Okay. The other question I could ask: who has greater linear speed? Okay, the same situation, but it's asking a different question. Linear speed is what you might think of as who's moving faster, not who's spinning around faster. In this case, your friend does. Why? Because they have to go a greater distance. They have a greater circumference compared to you in the same amount of time. Right? That's it. Your friend's going to go faster. You're on the outside of a circle. You're going to go faster than the people on the inside of it. Yep. Assuming you're spinning around the same RPM, the ball's going to go, well, it's a little tricky because the RPMs, you really got to be like, it's more like, because that's a tricky one, because I'm trying to think what's more like. What spins? I can only think of like a car tire right now that spins. Man, I mean, the merry-go-round is probably the closest thing I could think of off the top of my head. So, but yeah, I mean, whatever helps you remember it is good. It's true. You're not wrong. I'm just saying. So, summary. Be able to use the linear motion equations for solve for variables. All right, we don't have any angles or nothing like that. Use the 2D dynamics equations. That's these things right here. All right. I believe there was some on the review guide, so make sure you could do those. All right. If you got questions, let me know. I'll go back. Finally, momentum. Slide. Oh, we're almost done. Okay, we're almost done. Which has more momentum? Same question as before, it seems like, except in this case, I'm asking about momentum. Earlier, I asked which one has more inertia, and it was the bowling ball. Does the bowling ball still have the same amount of momentum? Bowling ball at rest or the small marble rolling across the table? Why? Well, momentum is mass times velocity. If the bowling ball is at rest, that means that's 0, and so the answer is not the bowling ball. Marble. Because the bowling ball is at rest, which means P equals whatever the mass is times 0. And anything times 0 is 0. It has 0 momentum. The small marble, it's got some mass times some speed, so it's got non-zero momentum. So there you go. How much force does a 5 kilogram object moving at 10 meters per second need to stop it if in 20 seconds? All right, so there's your equations from the equation sheet. We want to know force. We've got mass is 5 kilograms. We've got 10 meters per second. That's going to be velocity. And actually, it says to stop it. So the change in velocity is going to go from 10 down to 0. So that's a negative 10 meters per second. And the time is 20 seconds to do that. So what do? We want to know force. All right. Well, force is right here. This is what I like to do. I just like to, I know force. I want to find force. I know time. Time is given, 20 seconds. I know the mass, and I know the delta V. So I'm going to use Ft equals m delta V, that equation. Because now I can just plug in numbers and solve. So the force times 20 seconds is equal to 5 kilograms times negative 10 meters per second. I have a feeling that direction is not going to matter, which is the negative. So if I take, that's what, 50. So if I take the force is equal to negative 50 kilogram meters per second divided by 20 seconds. Seconds cancels out. Does seconds cancel out? No, what am I talking about? It does not cancel out. Maybe it does. Kilogram meters, that's not a thing. Oh yeah, kilogram meters per second ends up being Newton. They don't cancel out. They don't cancel out because they're both on the bottom. So the force ends up being 5 divided by 2. That sounds suspiciously like negative 2.5 if I look at my choices. Kilogram meters per second squared, which is newtons. That's a Newton. So yeah, the answer is A. Okay. The negative just specifies direction. It doesn't really matter. That's the thing to take away. Why is 10 a negative? I did it because it's stopping it. And so it goes from, so this is like my VI. That's my VI. Oops. What did I just press? That's my VI, and stopping it, the 0 is my VF. And so to find the change in anything, you take the VF minus the VI. How much do you have now? Subtract how much you had. And that's how much it changed. So it's like, I mean, how old are you? You know, if you're 15, and how much did you change since you were 10? Well, you are 15 now. You subtract 10, so you've gained 5 years. You know, so you take how much you have minus how much you had. So I put a 10 in there and all that does is indicate direction. It doesn't really matter in this case, but we'll keep it in there anyway. All right. the takeaway here is, the big takeaway is to use especially this big combo of equations. You just pick two things, like this and this, or this and this, or this and this, all of that, not just that little part, and this. Or like we just did, I chose this and this. You take two sets and you set them equal to each other. Okay. How much impulse does a 5 kilogram object? So it's the same stuff. So the same. It's actually not the same. I apologize. Let's just do this fresh. Impulse is I. 5 kilograms is mass. To stop it. So once again, our delta V is going to be -10. Doesn't matter if it's negative, probably not, but it's slowing down. So I'm going to say it's lost 10 meters per second of speed. Time is 20 seconds. Okay, I need to find I. Well, I need this one. There we go. Could I use this one? Like maybe, but I don't know F or T. I know T, I don't know F, so I can't use that one. But I do know M and V, so my equation I'll probably use is that, M delta V. I know I'm going kind of quick. You might not be processing exactly what I'm doing, so that's why I just ask, or just maybe go back and watch this again, because that will answer your question. So maybe. So mass is 5 kilograms. Change in velocity is -10 meters per second. Impulse is going to be -50 kilogram meters per second, which ends up being Newton seconds. But the units aren't super important because they're all Newtons here. -50. So the direction is negative, but it doesn't matter. It's asking how much impulse. It doesn't ask about direction. In this case, in my example here. So it is 50 would be my answer. All right. Right. I'll go back if you need me to. It's okay. How much momentum does okay, same thing. Now, how much momentum does I'm moving at, lose? How much does it lose? So it's going to lose some momentum. So P, how much is it going to lose? That's my question. So how much does it change? It's the same thing again. We got mass is 5 kilograms. I wish I could just kind of pull up the old thing. Delta V is -10 meters per second because it's slowing down. Time is 20 seconds. So now, once again, I'm going to look at my little equation here. It looks like I'm trying to find how much momentum does it lose. And I've got mass and velocity again. And so I'm going to use the equation here, mass times delta V. And I literally just did this one like the previous question. So like mass times delta V, I figured it out. It's 50. So I don't necessarily, I mean, if you want me to do it again, I will, but it's just multiplication. Again, the takeaway here is you list out your variables as best you can, and you basically try to see if you could pick two things that are equal to each other. That's all it is. So those two things are equal to each other, and set them equal to each other, and you can find it. All right. We have a little extraneous information. We don't need to know the time. Not important in this example, and that's okay. Okay, almost done. Why do you feel less force when the driver of a car stops gradually compared to when they stop suddenly? So this goes into the egg drop. And, I think when you see all the choice is going to be C. There's less force because of the extra time. More time means less force. Exactly. It has to do with this equation right here. More time, that looks like I'm pointing at I'm not. More time means less force. That's all it is. More time, less force. Okay. Why do we have airbags in our car? Because it takes more time for our head to slow down to a stop using the airbag than it would if it just hit the steering wheel and stopped suddenly. And so there's less force applied. Why do we have cushions on anything? Because it takes more time to, It absorbs the impact is what we like to say. What does that mean to absorb it? What all it means is that it takes more time to stop it, which means there's less force. Okay, the same reason we bend our knees when we land, or we catch something gently when we don't want to break it, because by increasing the amount of time it takes to stop, we decrease the amount of force necessary. The most tangible example I could think of is when you're in a car and the driver is going 40 miles an hour and they come to a stop. And if they come to a stop suddenly in very little time, you're going to feel more force. But if they go from 40 down to 0 gradually, you're going to feel a lot less force. That principle is what we're getting at. And that is the principle of impulse, where force times time gives you that impulse. All right, I guess I'll do this. So now we're getting into collisions. This is unit 4 stuff, so we just got done doing this. There's only a couple slides left, like literally one more example after this one. So 109 from the review guide. 2,000 kilogram car moving at 4 meters per second hits a 1,000 kilogram car initially at rest. The cars stick together after the collision. What will the speed immediately? What will the speed be immediately after the impact? Oh, there's a B. This is the one where you're going to have to make your data table, your chart. All right, your before and your after. Well, I guess you don't need to, but there's a reason I've been teaching you to do it, because it's extremely useful. I'll just say, so the momentum of car, I don't know, the 2,000 kilogram car, the momentum of the 1,000 kilogram car, and the total momentum. All right, and if you want to draw the lines, it's up to you, just for your own use, right? So in this case, before momentum, let's say P equals M times V. So we're going to take 2,000 kilograms times the velocity, which is 4 meters per second. And that gives us 8,000 kilogram meters per second. The other one is at rest. I'll write it out though, 1,000 kilograms times 0. And so the momentum is 0. So the total momentum is 8,000 plus 0. So it's 8,000 kilogram meters per second. And then as soon as you know the one, you know the other one right away, 8,000 kilogram meters per second. All right. And then after the collision, it's going to be the same mass. They stick together, but we kind of still treat them as two separate objects. They're right. They stick together. I just want to make sure they stick together. That's what we call a inelastic collision times some velocity. And they're moving together, so this is going to be 1,000 kilograms. You got 2.6. I wish I had the answer to that. I'm going in blind here. So the bottom line is this box plus this box has to equal this box. So 2,000 kilograms times V plus 1,000 kilograms times V, same velocity because they're moving together, is equal to 8,000 kilogram meters per second. All right, so we could add up the like terms, and we got 3,000 kilograms times velocity is equal to that 8,000 again, kilogram meters per second. And so now we got to solve for V, so I'm going to get rid of that over on this side, get rid of the 3,000 kilograms. That'll cancel that out, but whatever we do to one side, we got to do to the other. 3,000 kilograms. The kilograms are going to cancel out, leaving us with just meters per second, which is amazing. And let's see if you are right. So 8, whoa, hello, 0. Buttons. 8,000 divided by 3,000. 2.6. I'd round that to 2.7, but yeah, you're right. So 2.7 meters per second. That's the fast version. That's just me solving it, not really explaining much as I do it. Well, I'd explain it a little bit. Okay. Last one. I didn't find an example of this on the review guide for the final. That's unfortunate because you need to review it for the final. It's the same idea, but this type of question was not on the final. So I went back to the practice, number 24 from the 4.2 practice. Can you go back, please? Yeah, sure. Yeah. What you need? Just need a second? That's fine. I'll take a sip of water. La 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 la. All right. Okay. Okay. I'm gonna go forward then. Unless you got a question. I go back. One more question. That next one is the last one I'm gonna do tonight. All right. All right. Here we go. Sorry, shallow. I gotta move on. But if you want me to go back later, I will. So this is number 24 from that practice. And like I said, I should have put one of these on the test review because you're going to see something like this on the test. Okay, so go back and do these from, they're called explosions. I called them explosions. That's not how you spell explosions. What is this? I'm getting tired. Those are called explosions. All right, because things explode apart. Okay. You stand on a skateboard in a frictionless environment holding a 1.4 kilogram ball. The mass of you, the ball, and the skateboard together is 80 kilograms. You throw the ball to the, okay. I want to like make it clear what's going on here. So you're standing on a skateboard. All right, so here's a skateboard. Here's you. All right. And you have already thrown the ball. That's a ball. The ball is moving this way, you are moving this way, and the skateboard, all moving like this. You have thrown the ball. I need to stop drawing. That's hands. So you and the skateboard are together, all right? Which is why somewhere it says this. You stand on a skateboard. What is your speed? You stand on a skateboard. Oh. No, you gotta do a little math. All right. Together, all of you weighs 80 kilograms. The ball has a mass of 1.4 kilograms, which means that you and the skateboard together has a mass of 78.6 kilograms. I did that in my head, so I hope I'm right. Okay. Better check. 1.4. Yeah, 78.6. Okay. So now we set it up just like before. All right. We got our before, we got our after. We've got our momentum of, we'll just call it A, that's me or you or whatever. And then we got B, which is the ball, and then we've got our total. All right. So how do I set this? Before and after. That's what the B and the A stands for, because I'm getting lazy. All right, that's fine. So before, it says you're standing on a skateboard in a frictionless, you're just holding it. So you and the skateboard together have a mass of 78.6 kilograms. And you're just standing there. So your momentum is 0. You throw this ball, you're holding the ball at first, which is a mass of 1.4 kilograms. Also being held still by you. Total momentum 0. Okay. So momentum is 0 total. The total momentum is 0 after, because it doesn't change. Now here's the thing. You and the skateboard, 78.6 kilograms, are moving at some speed. Don't know what it is. That's what it's asking. It says you throw the ball at, it's 1.4 kilograms to the 12 north at 12 meters per second. North is a positive number. We're going to use positive numbers to represent north. So I'm going to keep it positive. Let's put a little plus. No, you know what? I'm not going to put a plus there because plus is always implied. I don't want to be confusing right now. The last minute. So 12 meters per second. Okay. Just like before, this box, the top box, times velocity, plus the middle box. Oh, I could actually calculate that. 1.4 times 12. I can't actually see it. 16.8. Okay, 16.8. Okay, plus, so now I don't need these parentheses here, plus the middle box, 16.8 kilogram meters per second is equal to 0. We must solve for V. There is no V over here. I cannot add them together. So what I'm going to do, I'm going to just subtract 16.8 kilogram meters per second from both sides minus 16.8 kilograms per meter. All right. I don't know why this box is there. It doesn't need to be here. Well, I guess that's important. So 78.6 kilograms times V is equal to negative 16.8, because this cancels out. We're left with this. Kilograms meters per second. All right, now I got to solve for V, so I'm going to divide both sides by 78.6. Kilograms. Now cancel that out over here, divided by 78.6 kilograms, cancels out the kilograms. Then we do our little calculation in the calculator. That's what it would be for. Negative 16.8 divided by 78.6. And I get negative 0.2, we'll just leave it at 0.21 meters per second. I can't leave it with a negative, so the final answer is 0.21 meters per second. What's negative north? Negative north is south. That is my final answer. That's how fast you're moving after you throw the ball on a skateboard. It's the same setup as the other ones. It's just that the momentum adds up to 0. Okay. Yeah, you'll have to do this one on the final. Not this exact one, but you'll have to do these kinds of questions on the final. So you'll have to do these maths. I highly recommend throwing together a data table like I just did. There's other ways to do it. You don't have to do the data table, but it works. It's just a way of keeping track of things. Okay. So I can go back if you want me to, but be able to know the difference between elastic, and inelastic collisions. Elastics bounce. Inelastics stick together. All right. Solve for velocity if they stick, bounce, or explode. Great question. Next semester, we're going to start talking about energy, kinetic potential energy, that kind of stuff, conservation of energy. We're going to talk about static electricity. What happens when you get shocked, when you touch something, you get zapped. We're going to talk about magnetism. We're going to talk about electricity, like electrical current. We're going to talk about sound waves and light waves. And that'll do it. It's a lot. So I'm excited. It'll be a lot different. All right. Stuck with me for, holy cow, this is my longest live stream review ever. Yep. So there's less than you might think on the final, but still got to prepare for it. There's less than you might have feared on the final. You could ask me any questions you want through your mind. You can ask me in class. But yeah, so I don't think there's any other questions. If you do, almost 2 hours. It's crazy. Nice job sticking with me. All right. I don't see any questions, so I think it's time to put a pin in this. All right. Hopefully this helped, and hopefully you have some like more direction of what to study and what not to study. All right. Well, you guys have a wonderful evening, and study hard, and then rest. All right. Take care. See y'all in class. Bye.